Welcome to our third video in the series of organic chemistry. Our today's topic is alkanes, physical properties, and isomerism. Let's start off with the physical properties exemplified at the property boiling point. We already know the four alkane molecules: methane, ethane, propane, and butane. You can see the displayed formula in the table. And each of these alkanes has got its specific boiling point. And what we can see as a trend is that the boiling point increases from methane to butane. Yes, because the negative temperature gets lower, this means the temperature increases, because -1 degree Celsius is warmer than -42 degrees Celsius. And what we can also observe from methane to butane is that the carbon chain length increases. So butane has the longest carbon chain of the four depicted molecules. And there's a very important principle in chemistry, and this is that structure determines property. We can see that an increasing chain length corresponds to an increasing boiling point. Well, why is this? To understand that, we have to look at the so-called van der Waals forces. How do they come into being? Let's look at the left. We have a random molecule, and in this molecule we have electrons. And electrons move constantly, so at a certain point of time, by chance, it may be that the negative charge is kind of shifted to one end of the molecule, for example the right side, and then we have a partial negative charge on the right side of this molecule, and at the same time, of course, a partial positive charge on the other side of the molecule where the electrons are lacking constantly. And this so-called induced dipole, this molecule with partial charges interacts with surrounding molecules. Because in the neighboring molecules, for example molecule 2 over there, we also have electrons, and they are repelled from the partial negative charge of molecule 1. So the electrons gather on the right side of molecule 2, and then we have a partial positive charge on the left side of molecule 2. And between the partial negative charge of molecule 1 and the partial positive charge of molecule 2, we have an attraction force. And that's the so-called van der Waals force, which kind of holds the molecules together. Now, why or how do the van der Waals forces differ within methane and within butane? So methane molecules are smaller than butane molecules. Butane molecules have quite a long carbon chain. We've talked about this earlier. And in this illustration here on the right side, we can see that the longer molecules, of course, are able to develop more van der Waals forces than small molecules like methane. So it should be quite apparent that butane molecules have more van der Waals forces between them than methane molecules, and that's why butane molecules stick closer together. There are more attraction forces between the molecules. If we want to reach the boiling point of a substance, we have to overcome attraction forces, yes? So in the liquid state, the particles still are touching one another, but in the gaseous state of matter, the attraction forces between the particles are entirely broken. So we have to overcome the attraction forces, and this is more easy within methane than butane, because methane molecules attract one another not that strong. And that means that we need a lower temperature to boil methane So the boiling point of methane is lower compared to the boiling point of butane. Let's talk about a second very important thing in organic chemistry, and that's isomerism. Isomers have the same molecular formula but different displayed formula. And we can see this below. This displayed formula has the molecular formula C4H10. And that molecular displayed formula, which is apparently different to the left one because we sort of have a branch over here, also has the molecular formula C4H10. And because they have an identical molecular formula, C4H10, but a different displayed formula, we call these two molecules, for example, isomers. And the molecular formula, thus, is an ambiguous description of the way atoms are arranged in a molecule, and the displayed formula, where all the atoms and all the bonds are shown, is an unambiguous description of the way atoms are arranged in a molecule. So if I only got the molecular formula C4H10, I don't know whether the left or the right molecule is actually meant. It's ambiguous. How can we name isomers? So we take the branched molecule from before. In naming isomers, we first have to find the longest carbon chain and give it a name. And we use the corresponding alkane name. In this case, the longest carbon chain is encircled with blue color, and it's propane because it's 3 carbon atoms. In the second step, we have to identify the substituents, and a substituent is anything except for a hydrogen atom. And the green encircled part of the molecule is the substituent. We have 1 carbon atom bonded to 3 hydrogen atoms. And the name of this substituent is methyl. And there's also a rule behind, which is more easy to understand if one has already learned the names of the alkanes. Because the part meth refers to the 1 carbon atom that is involved into the substituent. It's the same as methane. In terms of that methane also consists of only 1 carbon atom, and the YL syllable in the end indicates that this is a substituent. So that's why the name of this substituent is methyl. If we had 2 carbon atoms as a substituent with hydrogen atoms bonded to them, then the name would be ethyl, how you can see over there in the table. Okay, let's go back. Step number 3 to name the isomer is we have to number the main chain to find the position of the substituent. And the position should be as small as possible. So in this case, we could number the main chain like this. First carbon atom, second, third. We could also do it the other way around, so that could be also 1, but then this carbon atom still gets number 2, so it doesn't matter in this case. Whatever way we take, we find that the number of the substituent in this case must be 2, and this number is also important for the final name of the isomer, which would be 2-methylpropane. It tells us we have a propane, and at the second carbon atom of the propane, we have a methyl substituent. All right. In the end, we have to talk about some risks in finding isomers, because not every displayed formula that shows some differences to other displayed formula is automatically an isomer. First of all, we have to talk about a way of representation. These molecules, these 3 displayed formula that you can see are all identical. They are the same molecule. And this group, so that carbon atom with 3 hydrogen atoms, this methyl group, so to say, can be either represented very detailed. Here we can see all the atoms and all the bonds, or we can summarize this group as CH3. So that's the same, okay? And now the thing why all these representations are the same is that around single bonds, rotation is possible. And if we rotate around this CC bond between the second and the third carbon atom, then we will have the case that the CH3 group may be at the top in one case, or maybe at the bottom in another situation, or maybe also in the middle, and that would be this representation. It's a bit hard to imagine it because we are working in a two-dimensional field right here, but if we rotate around this bond, I'll highlight it in the other molecules as well. If we rotate it, we can imagine how the methyl group changes the position, but still it's the same molecule basically. That's why they are not isomers, these three formula. What we can also tell then is that the longest carbon chain that we need to give the name to the formula may not be in one line. In our case, the longest carbon chain, if we look at the second diagram, is found here. So it's not in one line, but it's still 4 carbon atoms that are connected with one another. So all the molecules are butane molecules. That's enough for this video. Thank you guys for watching, and I'm looking forward to seeing you in the next video. Bye bye.